Hello, this is video 78, the last video for our unit on fluids here. We're going to be talking about floating objects. So a floating object is an object in equilibrium. It's at rest floating on the surface. We actually saw this in a previous video where we had the ice cube that was melting. So when it's in static equilibrium, that means that the forces balance. That means that the buoyant force is going to equal to the weight of the object. B is equal to W. We just saw in the previous video that we could replace the buoyant force by density of the fluid, volume of fluid displaced times G. And then we could replace the weight of the object here. This is the weight of the object. We could replace that by density of the object, volume of the object times G. Just look at the previous video if you don't know where this comes from. So the G's cancel out in this equation. But this time, V fluid does not equal V of the object. This is only the case that they equal each other when the object is completely submerged. When an object is floating, part of it is going to stick up above the water. So V of the fluid displaced in this case would just be the volume of what's underwater here, while the volume of the object is the whole thing. So you can see that they're not equal to each other. And I would just write this down just as a recap of this. When an object is completely submerged, then the volume of the fluid displaced equals the volume of the object. But otherwise, if it's only partly submerged, then the volume of the fluid displaced is only equal to the part, and this is very long, that's why we don't write this out, the part of the object that is underwater. So just a recap so you know exactly what to plug in for V fluid here. So that means if they're not the same, that we can't cancel them out, but we can rewrite this as a fraction here. What I've done is I've divided both sides by V of the object and then divided both sides by density of the fluid to get this equation. So this is what I like to call a shortcut equation. And we can only use it if we have one floating object. If you have a floating object and then there's something that is stuck on top of it, then you cannot use this equation, because this equation was derived when we just had that buoyant force on this one object was balancing the weight of that one object. So just keep that in mind when you want to use this equation. You can only have one floating object. Let's look at an example using this shortcut equation. So you've probably watched the Titanic, and you know that that poor ship sunk after hitting the iceberg. And that's because a lot of the iceberg is below water and you don't see it until it's too late. What fraction of the iceberg is below water? Assume the density of the ice is 920 kilograms per meter cubed and the density of the sea is 1,025 kilograms per meter cubed. So the iceberg is one floating object. Let's use our shortcut equation that we just derived. The volume of the fluid displaced divided by the volume of the object is equal to the density of the object divided by the density of the fluid. We just talked about that if only part of the object is underwater, then V fluid is equal to the part of the object that's underwater. And I'll just write that as V sub. And that's going to be the part of the object that is submerged. So it's not the whole object, just a part of the object that is submerged. Look at what happens at our shortcut equation, where this is a rho, not a p here, density, that the ratio of the densities, the ratio of the density of the object to that of the liquid that it's in, is equal to the ratio of the part of the object that is submerged over the volume of the whole object. Can you see that this ratio is equal to the fraction of the iceberg that is below water? That's what this means. The part that is submerged divided by the whole volume of the whole thing. So the answer to this problem is simply to divide the two densities. The part of the fraction that is below water is going to equal the density of that iceberg, the 920, over the density of the seawater. And that ratio is equal to 0.9. So that means that 90%, or 89.7, or actually 89.8% of the iceberg is below water. All you have to do is take the ratio of the densities. So we can actually come up with an equation for this, the equation that we just saw with the iceberg. If you are trying to know how high does an object float, how much of the object is going to stick up above the water or below the water, well, it's going to have to do with the density of the object and how it compares to the density of the liquid. This is what we just saw in the previous example, the fraction submerged, the density of the object divided by the density of the fluid displaced. Let's take a look at how we can apply this. We have these three objects that are floating in the water. Which object is most dense? So we just saw that the fraction submerged is equal to the density of the object divided by the density of the fluid. So this gives us the fraction submerged, the part of it that's underwater. In this first one, it looks like it's about 3/4 of the way submerged. That's the fraction that's in the water. For the block B here, it looks like it's about 1/4 submerged. Block C, it looks like it's about halfway submerged. So, whichever has the greatest density of the object is going to have the greatest fraction, because the density of the liquid doesn't change. Can you see that block A, because it has the most submerged, that means it's going to have the biggest density of the object. The ratio of the density of this object to that of fluid is going to be 3/4. Can you see that this equation can actually tell us the density of your object? That means that the object has 3/4 of the density of the water. So if the water has a density of 1,000 kilograms per meter cubed, then that means that this object has a density of 3/4 of that, 750 kilograms per meter cubed. So it's a very useful formula that we have, that the fraction submerged equals the density of the object divided by the density of the fluid. Whatever fraction is below the water, that's the fraction of that density of that object to the density of the water. Let's take a look at one more question related to this topic. An unloaded ship floats higher in water than a loaded ship. The unloaded ship is the picture A and the loaded ship is picture B. Which one experiences more buoyant force? So you might be tempted to think, well, in A here it floats higher, so there's more buoyant force because it floats higher. But we learned for a floating object that the buoyant force is equal to the weight of the object. Which ship is heavier? The loaded ship is going to be heavier than the unloaded ship. So the weight of this object over here is greater than the weight of this object here because it's unloaded. Well, if the buoyant force equals the weight of the object, that means that the buoyant force for the unloaded ship is going to be less than the buoyant force for the loaded ship. So the answer is that the one that is actually has more of it in the water is experience more buoyant force, because that buoyant force has to balance the weight of the object. So just to recap, when an object is floating, the buoyant force equals the weight of the object.